So I'm Sumant Tambe, and I work for a company in California called Real-Time Innovations, and I'm here to talk about a new standard that we are working on. It's been actually finalized, called an API for data distribution service. That's what this talk is about. So just out of curiosity, so how many people have heard about DDS before you read this program or this particular presentation today? Interesting. So, well, that's why I'm going to introduce you where DDS is really used. You know, why does it really matter? So, my claim today is going to be that you are in fact a DDS user. You possibly couldn't have been here for this conference if there was no DDS. For example, DDS is used in air traffic controller systems. For airports, DDS has been used and has really strong presence in Navy, in Air Force, sort of defense applications worldwide, not only in US. DDS has been used is being used in healthcare, in cars. In cars these days, there are so many processors and so much happens at software level that it really blows your mind away. Air traffic again, factory automation, controlling these robotic arms, tracking locomotives. You know, apparently these really big locomotives get lost. I don't know how that happens, but they do, and they want to track them. Cars again, video processing. So there are plenty of applications. Go ahead. That's right. Yeah, that seems like kind of a flagship application, or really typical kind of application for DDS. So there is a commonality here. These applications are you can think of them as smart systems. Without these, life will be just like in Stone Ages. And what is really important in these systems is these systems deal with real world physics. There are timing constraints, real-time processing constraints, because an aircraft that's landing is not going to stop because you are doing a garbage collection or something like that. The real-time constraints are imposed by the environment on the software, and software has to work within those kind of bounds. You really cannot stop processing information. A failure in these kind of systems implies really bad things. People may die if these systems don't work as expected. It's one thing to lose money if an enterprise system doesn't work or it's down for a few hours, but here we're talking about life. You can think of DDS as it is a publish subscribe middleware. There's a standard for that, and there are implementers who implement DDS specification. You have some producing applications, for example, streaming data, some sensors, temperature sensors, or even radars, some events. And then there are some subscribing applications, real-time processing, enterprise applications, those are also possible, and actuators, kind of the robotic arm, like you sense something and you respond to that. Well, you've probably seen this architecture before. I'm sure it's just publish subscribe. What's new here? The new part is really, it's data centric. And I'm going to spend next 5 minutes on this slide trying to convince you that data centric architecture is really kind of really suitable for these kind of applications. So classic publish subscribe, another way of thinking about it is message centric. You're probably familiar with that. So in message-centric middleware, there are only messages, no concept of a data object. For example, a tweet or a purchase order. It kind of stands on its own. You know what tweet? Yeah, tweet is 140 bytes, and that's all. The messages in this particular middleware, right? They are not cached typically by the middleware. And what I mean by that is, there is some caching for performance reasons, throughput reasons, but that's not visible to the application. It's not the design goal of these middlewares to have application access a well-known cache of, well-defined cache of messages. That's just not part of the design. And I'll compare that how it is in data distribution service. You can have some QoS attached to these messages. For example, QoS is quality of service. I'm not defining that here. I apologize for that. It's non-functional property of a message, or of a channel between data writer or between a producer and a consumer. Latency is a non-functional characteristic, but that's not what I mean here. You don't specify that I want this latency. Latency is a result of your system. Here I'm talking about some filters, or you could specify that all messages that are going on this channel must be persisted in a database. That's a property you assign to that data flow for durability, lifespan, kind of things. In data distribution world, DDS specifically, there is a full-fledged data model of applications that are communicating. So here, I have some producers and some consumers, and the data that they communicate, they share, is fully described over here. So, and that data model is nothing but, you can think of them as structs, you can think of them as nested structs, and even inheritance. So those are kind of properties that can be captured in a data model, and these applications depend on that relationship. It's discoverable in a sense. An application here has visibility on, okay, what are other different types going on in the network, sort of, and you can discover different topics. I'm kind of maybe jumping ahead of myself here, but that's the idea. It's a data space, and you kind of operate off the data space. It's not like send message. It's really you update this data space with a new value, and it's not new really. Databases actually do this. Databases, classic relational databases, are a very simple example of data-centric. I won't call it middleware, data-centric system, where data comes first. You first define, altitude. This is, I knew this was going to happen. All right. So data comes first, and the applications, the behavior comes after that. And that, you do that in database design and applications based on that. The messages are actually in DDS represent a data object. So the best way to understand that is an example. So think of an aircraft, a commercial aircraft coming to an airport. When it comes within 10 miles of this airport, this new data object comes to life, that this aircraft is kind of around. It's coming towards this airport. And maybe next 10-15 minutes, it can kind of lives its life, the data object, it lands and then it arrives at the gate. And this data stream, that one data stream, kind of vanishes because its useful lifetime is over. Now there is a life cycle here, clearly. There is a creation of a data stream and there is a expiration, so to speak. DDS has first-class features or properties to really model that, or to discover that in a data space there is a new instance of an aircraft available. I mean, there might be hundreds of aircrafts in air at the same time, but is this a new one? Is this each aircraft forms its own kind of independent data stream, and you can easily model that. And you could do that using a key. It could be simply a GUID, a UID, and that's one way of doing it. The middleware also maintains the state of the object. Now this is really interesting. An application might be interested in, okay, I want last 10 values of each aircraft, that would be X, Y, and Z, its latitude, longitude, and its altitude, of all the aircrafts. It has some business with it. So I'm talking about these last 10 values. It could be 100, it could be N, could be different. So these kind of problems come up very often in the smart systems. So middleware has features that it kind of caches this information for the application to be available. when you read it, you don't kind of remove it from the middleware. It's still there for later use. Because as the window shifts, you might be reusing the same data for a while, and then it kind of goes out of window. In terms of quality of service, DDS really has lots of quality of service offerings, and for example, reliability, durability, history, and we'll talk about that. Any questions on this so far?
So it is typical middleware will catch mistake in some window of update, and you would set a policy as to how big you want that window to be.
Right. Could be 1, could be 1,000.
Right, and then the object life cycle comes, and then when it dies, is that typically archived, or what's normal?
You could. I think that should be possible, that the consuming applications can be made aware that, look, this particular aircraft no longer exists, and whatever that means in the context of application. This logical stream identified by a key has gone away, and that could be very useful meta information for applications to keep track of. One last sort of example, the conceptual difference between message-centric and data-centric. So you could think of message-centric as emails and data-centric as the Outlook calendar. So imagine you get on Monday morning an email. You are invited to a meeting on Thursday morning. Okay, you make a mental note of that. You go and do your work. Tuesday morning, you get another email. The meeting has been moved by an hour. Okay, that means it's Thursday, an hour later. Now, on Wednesday, you get another email. Wait. No, it's not on Thursday. It's on Friday, the same time. Now, when Friday actually arrives, you have to think about, well, hold on. I got first message on Monday. It moved 1 hour, and it's the same time on Friday. That means it must be whatever, 11 o'clock on Friday. So what's really happening here is you're going through this sequence of messages to reconstruct the whole state of where the meeting is supposed to be and when you should go. As opposed to that, in case of an Outlook calendar, it's like a data space. All you do is just go look up, and the meeting moves as per the messages it receives. So when the second message arrives, the meeting goes by an hour, and next day for the third message. So it's data-centric. The Outlook calendar is data-centric in that sense. All you have to do is just give me the latest update you have about this meeting. You don't have to reconstruct the state. So that's the conceptual difference here. Is that making sense? That's right. You just ask middleware, tell me about this instance, and whatever it knows, it will just tell you. Mind you, that's not the same as, it's not saying that it will be the same across the distributed system. It may not be. It's not like a database, you have a consistent view. In fact, DDS is eventually consistent, but that's okay for these kind of systems. I think you had another question. We can. I think the question is there less traffic when you use data-centric as opposed to message-centric? Not necessarily. It's really the view of the world. After all, at the consuming side, you need to get that update across. So it's just how the application, what application does to be aware of that new state. The messages go from here to here. Instead of the application, the middleware does the state construction for you as opposed to the application. But in this specific example, the number of messages will be the same. Although you could also think of a difference between a message and a data. If you want to send a difference between what just changed in a data object, right? The plane type, the make and build, it's Boeing 747, all that stays the same when it lands and when it goes to the gate. So you don't have to send that information over and over again. All you can send is send the delta. So that's the difference between a message and data. So message is not the same as data, because message is delta, and you apply it to what you know already, and that becomes your data. Does that make sense? Sure. The question is, if the middleware is keeping the history, then there should be some monitoring. Well, I don't know, let me try to answer it this way. It's not, the history is not unbounded. You specify some other quality of service properties so that the history doesn't grow unbounded, because that just won't work, you know. So I'm not sure that's what you meant by monitoring, or if I can paraphrase your comment, in message-centric systems, you need an external entity to keep the state. Maybe we can talk about this a little later. I am having, I have to go through lots of slides. We haven't even started talking about C++ yet, but sure, let's talk about it later. So that's the conceptual difference, and the API actually will reflect this philosophy, and that's why it's important to really make sure that I get it across. So DDS is actually a family of standards. The DDS, the system properties, and these the conceptual model was standardized in 2004. It doesn't talk about the API. I mean, doesn't talk about a language-specific API. I'll talk about it in a second. There is also a interoperability specification. So a DDS application working on one vendor's implementation works just fine with another application working on a different vendor's application. You're talking about APIs, API compatibility, so it's not only portable, but it's also interoperable. At the wire level, they know what you're talking about. So this has also been standardized. And it's really important, particularly defense world. There is UML profile, there is some Corba component model stuff, there are some type description facility. This is what defines the data model that's in the data space. And here's what we are going to talk about today. There are two APIs defined for two languages. One is C++, particularly C++ 03. There are some C++ 11 sort of provisions in it, and also for Java. There is ongoing work on security. There is also RPC or DDS. If you want to know what those are, come back at the end of the talk. So I'm going to show you different examples. So here is kind of a vocabulary. This is, I guess, the last slide, last kind of background slide before we jump into examples and real code. Here is a sort of the vocabulary for what's in DDS system. How do you create one? An application that talks over distributed over a network. So a domain participant, you can think of it as a process. It doesn't have to be really. You can have more than one domain participant in a process, but for our discussion, this is sufficient. This is like a process, and two processes separated by a network. You need a data writer. This is a publishing application, or maybe I should say producing application, and it talks to a data reader on the other side, and both of them use a type called foo. It could be user-defined type, some foo. There is a topic, and that is bound to this particular foo type, and you have to use this topic. Okay, I'm interested in whatever is being said on this topic. I know that's foo, so that's the way you kind of latch on to this topic. There are publishers that contain data writers, and subscribers that contain data readers, just kind of a parent-child relationship. There is offered and requested QoS. Now this is interesting. The data reader requests some QoS, quality of service. I'll show you an example in the next slide. And data writer offers something. So middleware actually looks at both of them and tries to see does it make sense for these two guys to talk to each other. If data writer is offering equivalent or stronger quality of service, then they will talk. Otherwise, they won't. And there is a callback-based mechanism to read data or read some system notifications, what's really happening in the system. Well, I think I had another slide in here, or maybe it's coming afterwards. Okay, all right. So why are we really talking about, why do we need a new API? The main reason is the classic way in which DDS has been defined in 2004 was UML model, and there is a interface definition language equivalent API for that, for creating publishers, subscribers, readers, writers kind of things. And there are well-known mappings from IDL to these languages. There are many more languages. The problem is that IDL is being a kind of a common denominator for all languages, doesn't recognize very powerful C++ or even other language features. For example, overloaded operators, static functions, templates, exception safety. In case of standard library, it doesn't know what STL is. It doesn't know standard string. So as a result of that, what happens is the old mappings, due to use of old mappings, the API you get to use DDS becomes really kind of, how do you say this, sort of old-fashioned. You cannot use really STL. It's not STL friendly. It feels foreign. It doesn't feel at home for a modern C++ program. And we want to fix that. And that's why we're talking about this standard. Question? I think, no, it's not the same, but it's similar enough to be confusing. Right. It does, yeah. Mm-hmm. Right. So the comment is there is a new IDL to C++11 binding, which will be one more arrow here. That can be used, but the result of that is still not what you want. You will see there are so many C++ specific. It's a design using C++ features that you don't derive even if you use ultra-modern mappings, because after all, your starting point is ideal. And you will see some examples. For example, operator overloading. There is just no way to describe that here. You are not going to get that in C++11 mapping automagically. So that's why we created this standard. We want an intuitive API, very easy to learn, easy to understand. It should be efficient, a very important requirement. It should be portable. It should be portable to the extent that it should be just sort of drop-in replacement of vendor implementation. So you just change the header path, change the libraries, your application compiles. That's the goal. And barring some extensions that each vendor provides, I think that's been achieved. So this API also allows extensions, and there are business reasons for that. We don't want to implement, if all the vendor implementations are exactly the same, then there is really no value add that each vendor provides. What we really want to do is a big chunk of the standard is implemented by different vendors, and then there are their own value add, which those are extensions. So this is well understood, and that's why there is a sort of standard way of providing extensions. Of course, it kills portability, but that's really the business reason behind having it. This is really the makeup of different companies that worked on this standard. It was finalized end of last year, December 2012. So other than RTI, there were several other companies, and it's a object management group standard. Okay, code, finally. So with all that background, let's look at how to write a really simple hello world DDS application using the new PISM, the new platform specific mapping. Maybe I didn't describe that, but the platform here is C++, and it's a C++ specific mapping. Java, that would be another one. So you create a domain participant. Well, first of all, there is a class track. I'll get to it, what that is, where that's coming from. You create a domain participant, you create a topic, and you say, it's really about tracks. Those tracks could be, given by radar or, whatnot. You specify a name for that. You create a publisher. Let's not go into details of why you need that. Now, before creating data writer, you want to specify some quality of service. What are the kind of guarantees this data writer is providing you? It says, okay, I'll write this data reliably. I can talk to you reliably. That means I will not drop any samples or anything like that. But I will keep only last 10 samples with me, no more. And durability is another QoS policy. I don't think that's really important for this particular discussion. But it says, okay, I'll be transient local. So yeah, let me just skip that. So now you create a data writer using, okay, this publisher, this topic, and this better match, this track, and this QoS. There you have it. You create a data writer, and that's kind of ready to start talking to whoever is out there consuming applications. You create an object of track. In this case, it's a tank type, and maybe its ID is dead, whatever, some data, and you write that. The key thing is this is not send message. You are sort of making this information available out there, that I know about this tank, this specific tank. It's an ID that you can have more information, of course, its location sort of, and you kind of write it to the data space. Now, whoever reads on the other side will get it, but it's not a send message. The name is purposefully like that. Mm-hmm. Sort of, yeah. When you write this, if this happens to be a new ID, the middleware will recognize that now this data writer is talking about a previously unknown tank. That means let me publish first of all that there is something new, and here is data about it. And then there are APIs to say I'm done talking about this guy. So that's again meta information that goes across the network. A very good question.
When you say new ID, that applies to all track, or is it some global uniqueness?
Only track. Yeah, the IDs are scoped within a type. You don't have to have an ID, but in most cases in DDS you do, because you want to distinguish between these sort of logical streams. So the question is it important? Do I have to make sure that I'm the only writer about this particular tank? The answer is no. In fact, for redundancy, you could have multiple data writers writing about the same instances. It's up to the reader to really, in fact, the middleware doesn't care. There is a QoS, I'll talk about it. For reader, there might be redundant updates. But that's maybe okay, this tank kind of moved a mile, then another mile. You get those updates redundantly. That's probably okay, because there is no behavior attached to this message. It's just, here is the state of the world. Here is the state of the world again. Here is the state of the world again. You get it multiple times. That's maybe okay. It's not like, I don't know, destroy tank. Not having that multiple times would probably not a good idea. But the key difference is you are attaching a behavior with that message. Destroy or something. This is just about, this is what I know, kind of. Does that answer your question? If you use a specific QoS called ownership, the writer says, okay, I'm kind of a big boss here. My ownership is 100. Your ownership, your other writer, you are 10. Then the reader can say, I want to read data from whoever is the boss. And there you have it. Then the middleware will say, okay, I'm going to throw away what this guy says, but later on you could in fact bump up its ownership strength to 200, and suddenly the data reader will switch its source. And here's data reader, some boilerplate code at the beginning. Let me jump to the QoS part. And here it's saying, well, it's okay if you don't talk to me reliably. I'm sort of best effort reader. As long as you keep last 5, I'm happy with you. And this is the same. Now, these QoS are not exactly the same, but the writer is offering stronger guarantees than what this guy needs, so they can talk. The middleware says, okay, you're good to go. Now you create data reader just like the data writer, and you read, and you get some data, whatever is available, and you can use some classic STL algorithms to do something with it. Now this wouldn't have been possible before in the earlier kind of old binding. Again, these overlaid operators, they are sort of I don't know, they are what's the right word? Not everybody likes those, but I like those. I mean, these are that kind of reads really well, in my opinion.
Quick question.
Mm-hmm.
In the previous slide, track, class track, you said it was often generated.
Right.
Considering this is the shared object between domains, it's generated by the IDL.
That's right.
So
It's
there's some IDL compiler in that.
that's right, and I think that's my next slide. Here you go.
Okay.
So here is the, well, I call it a radar track here, but it's track. So this is how you describe. This is IDL. This is not C++. And okay, it has an ID, latitude, longitude, altitude, and some sequence, some metadata with it. From this, you generate some C++ type that kind of captures the provides the necessary setters and getters based on the names here. And the implementation of this class is up to the implementer. All standard specifies is what should be the API, not how it should be implemented. You could have just a pointer and have a C struct, or you could have all the strings and everything spelled out in this class. It's up to you. It's up to the implementer. So there are several QoS. I'm not going to go into details of this. Of course, the standard recognizes that beyond just standard QoS, there are two kinds of extensibility that is required. First is, for example, even RTI provides some extensions for these standard QoS policies. There are certain members in some of these QoS policies that are non-standard. And then there are certain more QoS policies that are nowhere to be found in the standard. For example, reliability. In case of RTI, we provide additional member called max blocking time. Another one is acknowledgement kind. These are not specified in the standard. We want to keep them there because they are really useful. They are there for a reason. But what standard does is provides a compliant way to access those. So now, if you look at source code, you can see, and it's just actually an arrow operator. It's an overloaded arrow operator. For extensions, you have to use arrow operator. For standard defined things, you have to use the dot operator. So dot really allows you to have the interface in standard defined headers. Arrow allows you to kind of escape to some totally different pointer, which is generally implementation defined, and there could be any number of additional extensions. And other than that, there are certain QoS on top of that. For example, thread pool, batching kind of properties. So how do you specify these? Or in standard wants to specify a framework to really specify these. The way we do that is using templates. Pretty straightforward template code compared to all the different talks going on in this week. Actually, really, I mean, this is like no-brainer templates. So these are the setters, these are getters, and this is standard specified class. And it says, okay, if you have some policy type which I don't know, that's a template, and it could be arbitrary policy. The implementation of this, it kind of forwards it, kind of delegates it to the, over here, there's a delegate type, which is implementation defined. So if there is a policy that not supported in the standard interface, it implicitly needs to go um, to the underlying delegate, which needs to understand what that is. So these are sort of new types. For example, batching. You can have an object of type batching. Well, I don't think I have a good example here. These are really standard types, policies, but I think you get the idea here. So you could also read the data kind of back from QoS in H object. This gets populated, and you can also read deadline if you want. You can chain these. You could have some extension also. It will just go blend right in, but that's an extension now. Or you could use other policy objects also. It kind of gives consistency as well as a well-defined way of adding extensions, because if different vendors come up with really radical ideas of having extensions, because you can do certain things in so many ways in C++, we kind of restrict that here. All right. So now we're talking about how this philosophy of data-centric architecture kind of influences the read and take API. So first of all, there are two things in DDS: read and take. There are two different things. Read means, well, I want to access this data, but don't delete this from your buffers. I may need it again. And take is more like you're probably familiar with. You just take it once and it's gone. You have it with you. Clearly, if you keep doing just read, the buffers will grow because you're really not clearing the buffer space. But then there are other QoS policies, for example, resource limits that will limit how far it will grow. The interesting thing is what you read and how you read. Let me emphasize what I mean by that. So in case of data-centric kind of mindset, let me just look at these red sentences, and those should kind of give you the semantic differences. Have I read this sample before? First of all, there is read, which doesn't clear the buffer. So you might want to know, first of all, is this new data first of all, or is this something I have read before? And middleware can tell you, hey, yeah, you actually read this before. So that's that. So what's the state of the sample? Now this is something I think we already talked about. Is this a new tank, or is this something I knew already? The middleware can provide that information too. That you're really looking at a new tank, and if you want to do something about it, do that. Now you can also test is there anybody out there who is still talking about this specific tank or specific aircraft? These are kind of conceptual questions. I'm not going to show you the gory details of using API to do that. Actually, it's reasonably straightforward. But I want to give you the mindset, the kind of queries the API allows you to do. Over here, you can actually pass a full-fledged expression which looks like a SQL expression. Give me all the data about tanks that are within, I don't know, maybe 10 miles of this latitude and longitude, X and Y. So you form this query, and because the data is cached in the middleware, it's just like you could think of it as a database query, but there is no persistence here. All data is in memory. So this is kind of questions you want to ask when you develop your systems. But how do we do that? So here is an API for read and take. This is how you read it. For example, here you return some lone samples. Those are basically buffers to the underlying middleware. These are forward iterators. These are back inserting iterators. So this is how you read it. This still doesn't specify what you want to read. Those query kind of operations. So to capture that, wow, what just happened? I think I ran out of battery or something? No. Wow. No, actually my computer rebooted. Maybe it's I don't know. It's just decided to go to sleep. I hope not. I hope not. Starting Windows, I really apologize for that. maybe we could still talk about it, So what we want to achieve is, separate how you read from what you read. So you specify what you want to read you form a query object. We do that using selector. So the earlier questions or the sentences I showed, there is an API to kind of form this state. Okay, I want to use this query, and I want to use this specific instance, for instance, this specific ID. You kind of build up that state. What you want to read, and then you kind of pass it on to one of these read or take calls. Okay, here's what I want to read, and this is how I want to read. Okay, push it back, use pushback on a vector, or maybe fill in this range using forward iterator, or simply give me pointers to the underlying buffers. So those are kind of different ways of accessing the data. Question?
So given that API, it looks like the client really has no responsibility to remember if it read that item before.
Absolutely. That's
The middleware is recording all read transactions for each client, so that the client comes back saying, give me the way it is, or give me everything since the last time you saw it. The middleware tracks that.
To paraphrase your comment, the middleware is tracking the transactions that are going on between the client and the middleware regarding what data has been read or not. And the answer is yes. Clearly between successive function calls, that's obviously there. Across the life cycle of the reader, if this reader completely goes away, the process shuts down, comes back up. Now you are talking about you have to specify some QoS objects now, some QoS policies. For example, one would be durability, and in that case you say, well, first of all, and also history. So you could say, okay, I want to read last 10 values on this channel, provided its durability is transient local. In that case, you won't get anything till it has filled in its cache. The middleware kind of waits to get the latest 10 samples, and then read succeeds. So there are more details to it, but that's the basic idea. But you got it perfectly. That's how it's supposed to do. This is going to take. This is really embarrassing. Getting there. So that's the main difference. So the way we achieve that is using a very simple C++ technique. You return for a selector, you kind of build this state. You want to achieve this using method chaining. You kind of call the same different functions on the same object. You achieve that using returning the same object over and over. Is this one? No. So here, the instance remembers the handle and returns itself. The content sets this, returns itself. So you build this state, and I think this helps readability quite a bit. The main use of this is you don't have to have n multiplied by m combinations. There are different combinations here, different, how and what you want to read. So I think this is just what I explained. Instance returns the same object over and over, so you can kind of chain those methods one after another. Is the same object you are modifying. So you can actually, you need only n plus m combinations as opposed to n multiplied by m. If you didn't do this, you would have multiple functions with different parameters, with max samples, with instance handle, with query, without query. You see what I'm saying? So that's the reason. So this particular simple C++ feature helps us design, separate what and how in kind of a very readable, neat fashion. I thought you had a question. That's right. Yeah. So there is only one history per topic per instance for data. Yeah, the question is if there are multiple data writers. Right. The question is how can middleware, is there a facility to specify that don't repeat what you already told me, although keep it around. One way to do that is just take it out. That's one simple way. If you do read, it is also a way in particular that would be sample state actually. You specify sample state that being not read in this function. It's not really, well, yeah, actually this example does that. So state, what I'm interested in is I want new data only that I haven't read at all. So it will keep the data around, but it will only return you data that is you're interested in. And you know, this application thread may be interested in new data. Some other application thread may be interested in everything, old as well as new. They are sharing the same data reader. That works just fine. All right, the listener. So in DDS, there are listeners, first of all, to read data. It's a callback based mechanism. You just get data in your callback. Or you get a notification that there is data available on this reader, and then you do a read the way I showed earlier. Or you can also get some system notifications. So those are sort of, okay, did I just miss my deadline? Or in case of writer, am I really doing what I'm supposed to do? I should be writing data every so often, periodically. In case of data reader, did the offered deadline missed? What really happened? If that happens, I want to know that it actually happened. It's kind of system level notification. Did liveliness of the other side change? This writer I'm dependent on is no longer alive. Maybe it failed or something happened. I want to know about that if that happens. So these are kind of API callbacks you can implement and respond to that in DDS. These are standards based. These kind of systemic issues come up very often because reliability is very important in these systems. And there are about 5 or 6 in data reader. So the way we model this is, okay, listener is a base interface, and these are sort of worker listener instances here. In fact, interfaces. The methods are defined here, and this is kind of your first line of defense against some system notifications. And you may want to have different behavior based on what type and topic you are dealing with. If you are talking about some food topic, some chat, then maybe it's okay if you miss a deadline or if you missed the other guy is no longer alive. If you're talking about a topic, nuclear missile, then maybe not. Maybe you really want to do something really quickly if you missed a deadline in case of that. So there is a sort of escalation process. If at this kind of worker level or first line of defense really cannot do much for you, you sort of escalate this to your bosses or all the way to CEO here, the domain participant, that do something about it. I don't know. The liveliness change. I don't know what to do. This is one convenient place to sort of, it's a catch-all for different system notifications. So these interfaces inherit from these interfaces. The intention is the concrete instantiation would take care of the system notifications in the system. However, these are typed. These are actually modeled as they take template types because it's for example, for data reader, it's reading data of what kind, and that's why it's a template. But these guys are not. We'll come back to it in a second. So these are untyped. These are kind of generic actions. So here is the API. I don't. If it's okay. It's okay if you can't read this. If you can read this, that's great. So here is the data writer listener, which is type. It's a template. And you have these virtual methods, okay, deadline missed, incompatible QoS, and so on and so forth. You should implement those if you're interested in these callbacks. And here is the writer on which sort of the event happened. So you get that data pointer or some handle. The problem arises. Yeah, go ahead. Question. Well, it's a matter of having an adapter class which kind of provides empty implementations of these, and I think in the new standard those are called no-op listeners. So there is a no-op data writer listener. You inherit from that, you get empty bodies for all of them, just like adapter pattern in Java. So the question is, there is a C++ issue lying here. The escalation classes really don't have information about type. I mean, you cannot really, you have to implement this exact function in the derived class, but there is no type information there. There is no T. So how would you implement this function if you don't know what T is in case of these guys? And that's the problem we face. We still want to keep type here because you can do type specific actions, right? Whether it's a missile or it's a chat, it's different. The severity is different. But here, there is no information. Well, okay, I showed you an animation a second before. Anyway, so I have a little animation for you. What we do is we replace the sort of these first line of defense, the worker interfaces by any equivalent. It's similar to, it's actually type erasure, just like in boost any or I think even iterator, any iterator library. So once you have any, you kind of erase the type, and I'll show you how that happens. These more list specific classes can actually implement that. The type is hidden behind the any listeners, but you can still access it provided you know the ID and so on and so forth. You can do some runtime lookup based on IDs and do the right casting using any. I think looking at code would be much easier. The any data writer in this particular case provides some API that is independent of types. All data writers can provide this information. In case of readers, there is similar. But you cannot read data because data is typed. You cannot read unless you know the type. So you really have to cast before you can use this to read and write. So the type is erased. So the way we want to implement this is we want to hide the type for momentarily, but keep it there actually. You don't want to forget it at all altogether. So the way we do this is really classic type erasure implementation. If you're really familiar with it, I can probably skip this. If you want me to go through how it's done, it shouldn't take too long. So any data writer is not a template, but the constructor is. And you pass in any data writer. Now that this any is different any, let me say A. You pass in a data writer of some type, and you create a sort of a placeholder for this data writer. I'm going to show you this class in a moment. So the data writer holder is templatized, so it knows its concrete type, but it is inheriting from data writer holder base, which is not a template. And here you have the base pointer only. So by means of polymorphic assignment, you create a derived object here and you put it inside the base pointer, as simple as that. To get the original type back though, you have to specify the type. And you do dynamic cast in this particular case because you better be right in this case, otherwise dynamic cast will fail and you will get a null pointer, but that's okay. You have to keep track of types because you just erased it, you need to get back. You should specify the right one. So the implementation of the placeholder is pretty straightforward. these are sort of type independent operations, and inside the holder is simply a copy. In fact, this is a these are reference types, so it's really not making a copy of data writer, it's just a reference, like a shared pointer. And you keep this around, and you get kind of type erased data writers. And because of that, you can now inherit, so this particular functions, instead of taking a type data writer, now takes any data writer. There is no type information there in statically, and this guy is just happy because all you get is any data writer. Does that make sense, how we use the type erasure in this context? All right, moving along. So the next topic I want to touch upon is exception safety. This is kind of really interesting, really interesting in my opinion. So because we are specifying an API, and being a C++ enthusiast, I really want to ask myself, is this exception safe? I mean, what are exception safety guarantees? And if you step back, it's actually really important for portability. I think exception safety is a contract that can affect portability in major ways. If the specification cannot specify whether it is basic exception safe, strong exception safe, when you do actually port your application from one vendor to another, you may or may not have those guarantees, and that means your application behavior is suddenly different in case of exceptions. So, and you probably don't want that to happen, because exceptions in a smart system, kind of critical system, is a very important, you don't just hand wave in case of exceptions, because something bad is happening, there is life at stake, you really want some guarantee what's really going to happen. So this doesn't happen so often, but it's important to specify what will happen. Well, so let's look at read. And in this particular case, I am using back inserting iterator. So this particular function will push back the data that you're interested in into a vector or list, whatever you have. Clearly, it can fail in two places. The copy assignment operator of the data that you're copying can throw, because this is growing the, and the next one is pushback. Pushback may throw because the container may grow, may need to allocate more capacity as it's growing, and that operation may fail. So now you're talking about two things actually. Exception safety, not only for the application, but also for middleware. So first of all, what happens to the standard vector that was passed to this read? What happened to its old data? Is it all gone? Is it corrupt? Half of it is good, half of it is not. That's weird. But also at the middleware perspective. So you read this data, now you are copying this into your data structure. What does it mean? Did you read it? Did you finish reading it? Going back to your question, does it remember whether you finished reading or not? The next time around, what should I do? Well, you failed while copying, but really you did access it. So there are some really thorny issues that we encounter in this particular case. The key point here is there are two perspectives. What happens in application? What happens for application containers? What happens to the middleware? That's the key point I want to get across. So I have a little graphic for you to show, but a bit of background before why this is important. So again, this standard recognizes that, thank you, the underlying implementation may not be C++. In fact, this is just not supposed to be. You could implement entire DDS using C++, C+11 if you want to, but that would be a humongous task. And as vendors, we don't want to do that. This is just a layer, and that's the typical approach most vendors will take, on top of a C implementation of the middleware. It could be C++, doesn't have to be C, but the key point is there is existing investment in the implementation, which we just want to reuse, add a layer on top, and there you go. From top for the application, it looks like you get the API. I mean, this is classic adapter, right? Classic facades. So for this C layer, when you read something, as far as the middleware is concerned, this is really the middleware boundary. And everything above is really the application for this guy. Well, you're right, there's a layer here which is technically, conceptually still part of the middleware, but not for this layer. You know, it has been developed, it's mature for years. So let's see what happens when you do this. So you're running read. You get pointers to the underlying buffers, and you copy them. So you get it from the first layer back. And as far as the middleware is concerned, the data has been read because this operation succeeded. And the middleware marks this data as read. You know, so read, kind of counterintuitive it is a destructive operation. It changes state. Read changes state because you are marking not read to read. So that's what middleware is doing here. Okay, I'm done. All side effects of this operation are complete. You read this, successful. Great. But there is more coming. The application hasn't received data yet. This interface is kind of old style API, which you don't like. That's why there is this API. Now it's our time to kind of copy this back into a vector. You're doing pushback one by one. Well, you kind of push back maybe first few. You got an exception here for whatever reason. The vector threw an exception, maybe the copy threw an exception. Now what do I do? According to the middleware, you have finished reading it, but the application, it's clearly wrong, right? The application hasn't read it. The data is kind of stuck in the middle. Application kind of forgot, what happened to it. It doesn't care what happened to layers above. So what do? You could roll back. You could ask the middleware, well, I couldn't really copy this. Take this back. Take this back. Kind of roll back. But rollback would require, it's kind of a transaction now. This whole thing needs to go in a transaction, and that means you are really constraining the concurrency in it. Because while you are doing this, there could be another thread that's just sitting duck because you are copying data here. That's not what we want. So it will really reduce concurrency. This has to happen atomically if you want rollback semantics. But it's really not, that's not the problem here. Actually, the problem is about how it's really not exception safe. The API is not exception safe. That's the problem. So is there another way to around it? That's the question. Well, so let's consider some alternatives. Let's not use iterators. Just go back to the plain old kind of pointers to the underlying buffers. Well, that's the reason why we started doing all this stuff was to get kind of new style API, kind of friendly C++ friendly style of using it. So well, that's really not an option because otherwise everything is moot. Now let's consider if we could use RAII, because this is kind of resource management question. How about we create a samples class that keeps the middleware buffers with itself. It's a resource. It's kind of it's a resource that you keep around, and when the samples go out of scope, you will return it. It's just classic RAII pattern. Well, this function is actually returning it. That means you better have a copy constructor and assignment operator now, because the destructor is going to return those back to the middleware. It's done because it's doing buffer pooling. Buffer pooling is really important because we want efficiency. We really cannot allocate. We want to reduce allocation as much as possible during this fast path. Read will be called very often. We really don't want to pay cost of allocation every time we call read or take. So can you do copy assign? Well, yes, you can do that. But every time you read, that means there will be a copy made over here, and that copy will be allocated, because that's how RAI will work in a resource management class. So you don't want that either. Remember, this goes back to, it's not only efficiency reason, it could be just wrong, because the samples copy constructor could throw. That means you're back to the same problem. It's no different from why stack has two operations. One is top, another pop. If pop returned the object and the copy constructor threw, then you really lost the top of the stack, but the application doesn't have it. So that's the same problem here. So that's why it's been divided into two, but this operation, this particular example doesn't work here. We have a better solution than that. Does that make sense why this analogy kind of applies here in case of exceptions? Because right at the boundary of the function you could throw, so you don't even know whose fault that is. Is it the function that's at fault? Is it the samples? Is it the caller? What's really happening? Basically, this is also not exception safe. And the same reasoning goes on that. Well, let's see if we could use shared pointers, right? Once we create the shared pointer, you can just pass them along freely. There is very little, no risk at all of exceptions once a shared pointer is formed, right? It does allocation at the beginning, but not later on. So we read at the beginning here, and provided we have some data, we allocate a shared pointer and return that. Well, I'm using shared samples. It's kind of, think of it as a shared pointer really, but more tailored towards DDS. Internally it uses shared pointer, to think of it that way. Well, the problem here is, it's no different from the earlier case. The shared pointer allocation could fail because internally it allocates a reference count. Now that could fail. Is the same problem, it's just that it is inside read. You could in fact do some cleverness here. In cases if it fails, you could roll back, but it's really not the point here. It's the same problem we are encountering. So how about, actually this particular code violates the basic rules of exception safety. Have all the code that may throw at the beginning, and everything that does not is guaranteed to succeed towards the end. So let's do that. So let's, first of all, the first thing we do in read is allocate a pointer, so that if that fails, we don't read, life is good. There is no confusion about what happens in the middleware. We just get an exception back. But the problem here is, in most cases, this solution would suffice, but not in DDS. Each read does an allocation now. It's bad for two reasons. First of all, we don't want allocation. And second, you may not have anything to read at all. It does not say anywhere in DDS specification that every call to read will have some data. You could just get empty set, that's all. There is nothing for you right now, because the way you selected what you want, you could just get empty. That's not uncommon at all. So you just paid a heavy cost just to find out there is nothing for me. So it seems like even this solution is quite suboptimal for our case. Does that make sense so far? So what we ended up doing was we introduced move semantics. We use move semantics in C++ 03, by the way, to get what we really want. So we introduced a class called loan samples. It's basically a wrapper, an RAI style wrapper around these middleware buffers, pre-allocated buffers, to get data from inside layers to outside, and still keep the look and feel of modern C++. That means iterators and RAI and stuff like that. Loan samples does not do sharing. It only moves data from right-hand side to left-hand side. And that means when you return a loan samples object as by value, you are really taking the resources, stealing the resources away from the callee, from the inside function, to the caller. It kind of moves them. It's no different from shared pointer actually, but it is safer than that. I'll get to that. Not a shared pointer, auto pointer in C++ 03. So RAI is still applicable. So when the last reference to, when the last lone samples object goes out of scope, the buffer is returned back to the middleware, just like in case of exceptions that will happen automatically, but you don't pay a cost of copying. And the way it happens is because of move semantics. It has an internal resource that gets moved. So instead of let's just jump into code and see how that actually works. So here, fortunately, it fits in one slide. It's very interesting and kind of powerful feature, pretty simple to understand. Uses kind of nice C++, corner cases, but kind of works really nicely. So first of all, it's a template, and inside that you have a proxy class, a really simple class, just meant for sort of transport. Really no meaning attached to it. And you have a copy constructor and a copy assignment operator that is private. And by the way, this is a copy constructor, although it doesn't have const, it is still copy constructor as per the language rules. In fact, if you add any const qualified, CV qualified stuff here, it will be still a copy constructor. And that's private, so clearly we don't want compiler to use that, and it's just a declaration, no definition required. So when you actually, let's take one example. When you return, let's take an assignment of one lone samples to another. This one is private. So if you have, maybe I have an example afterwards, yes, precisely. Let's take this example. You have a named lone samples object that you want to assign here. That's not going to work. To make this compile, the compiler will look up this function and will say, sorry, that's private, can't use it. But if you add this, a move, then compiler is happy. What move does, just one line at the bottom here, it turns this named object into a temporary object here. The details of this we're going to see what this one-line code does. So now this is a temporary, and here you are now assigning a temporary to left-hand side. Compiler tries to see if there is a set of conversions that can be used to achieve that. And there is, in fact. That's what is happening here. The first thing it does, it recognizes, well, if I somehow get this proxy T, then I can kind of do this assignment. Well, actually, this particular one. But how do I get proxy T? Well, it looks at it here. Well, I can convert a lone samples into a proxy, and I'll just call this. I'll just call that. There is a sequence of implicit conversions, and there you go. That's what it does. This operation is kind of the crux of move. When you turn a lone sample, a valid lone sample, into proxy, you steal its resources. You make this resource equal to 0, and you push that into this resource. It's just a simple pointer, nothing more than that, and you return that. Very lightweight operation. And you pass that here, and it simply assumes whatever value it had. So through this conversion, actually, is the same thing that's happening here. There is a named variable, and you turn it into a proxy, calling this, and turn it back into lone samples using this, and you return that. So it's just spelled out, but because the way it is arranged, primarily because this is private, these public operations, now you have much stronger and safer what's the right word? Object, or class, move aware, or move only, I should say. It's a move only type. You cannot really copy. You don't get these semantics with standard shared pointer. Thank you. This makes sense in case of generic code. In some generic code you have assignments. You don't know what type it's using. If it happens to be lone samples, it's not going to compile, because unless you explicitly write move, it's just not going to work. And kind of the same principle applies when you have a function that returns. You create one, you have to move it out of the function. And same goes for sync. If you want to call call sync, you really have to say, well, yeah, move this inside. I know what I'm doing. Without that, it's going to fail to compile. So you have to explicitly say what you want to do, because this is destructive, right? Once it goes inside, the original has default state, which is equivalent to null pointer in this implementation. So the state of this is well defined after that, but it's unusable. I mean, it has forgotten what it had completely. Does that make sense? Any question on this so far? So that actually took care of, we don't allocate, right? I mean, in this particular implementation, there's hardly anything going on. No allocation, nothing. It just works pretty seamlessly. And in fact, I like that you have to write move because it's explicit. And that takes care of it. It is perfectly, usable after once you receive it, you can call begin and end to use your regular STL operations, STL algorithms. Only limitation in C++03 is that you cannot use this type to create a vector because it doesn't know what assignment is. Just like you cannot use an auto pointer in C++03 in a vector. But that's okay. We provide another class called shared samples. You turn these lone samples into a shared one. It's just like turning a auto pointer into a shared pointer. Same idea here. And then you can use vectors to your heart's content. But of course, when you do this, now you do an allocation of that little reference count. But now it's up to the programmer. Do I really want this? If you don't pay the cost for creating a reference count. So in our case, with this shared pointer, well, this move constructor idiom really helped us quite a bit to kind of get what we wanted with practically no effect on the interface. Clean interface with clean semantics. All right, so in last, unfortunately, well, I have 10 minutes, maybe I need 15 minutes to go through remaining sets of slides, but we are approaching end of my presentation. We do some special provisions for C++11. Well, when we started work on this back in 2008, C++11 didn't exist, so we couldn't really commit to C++11 at that time. But when we finalized, that was end of last year, clearly C++11 was there. There were questions, which C++ are you supporting? So we thought, yes, maybe we can do some syntax compatible extensions, support those for those who use C++11 environment. It's not very many, but there are some kind of important ones. Well, the first thing is we don't need to use this idiomatic way of using lone samples. We could just use first class smooth semantics, R-value references to implement this. That's the first provision that it's not mandatory. You could use it. It makes sense to use it for the implementers. Well, we have some free functions to make lone samples work seamlessly with range-based for loops. This begin, end are sort of the namespace level functions that come along with lone samples and shared samples. So you can actually iterate over your samples in a range-based for loop. So as long as you have begin and end and it has iterator semantics, this will work seamlessly. The DDS array is a template for standard array, template alias actually. It's the same as that. In C++03 is the identical API. It kind of behaves just like it, but here is just an alias, as simple as that. One more idiom that we found really useful, in C++11 is type-safe enumerations. In fact, all QoS policies, for example, durability here, there are these, well, maybe I should use this example, C++11. All these kind of enumerations are strongly typed, and that's why you can step away from the issues of good old enumerations, which are sort of scoping issues and some really funky expressions it participates in in Boolean context when you want a Boolean result. This takes care of it. But how about C++03? Because ideally we want to make this transition. Those who implement C++03 today, tomorrow this application wants to move to C++11. We want to lessen the burden of syntax changes. So in fact, we can get very close to the semantics of types of enumerations in C++ O3 using, well, an idiom by the same name. I'm not going into details of it today. You can look it up by just, types of enumeration idiom. But what it really does is a template that allows, scoping of these constants, as well as it makes a separate type. So, each safe enum this becomes a separate type, and that's why you get kind of type safety. Maybe I'm jumping too ahead, but the idea is for each enumeration, you create a different type by instantiating this, and you also provide, comparison operators, equal to, not equal to, all that stuff. And the result of that is syntax compatible types of enumerations. So this is how you scope it as well as use the internal constant. Earlier enumerations you would just use keep all. That's all. There is no scoping here. So this idiom allows us to achieve both, achieve that in C++ O3 environment. Any questions on this so far? Thank you. The comment was, it's a very good idea. And I said, thank you. Okay. So just touching upon this another standard at OMG, Object Management Group, ideal to C++ 11 mapping. Jeff brought it up a while ago. This is really a new mapping defined independent of Corba, of ideal to C++, 11 particularly. You could use this technically to, this generator that implements this on the API, the DDS API that's defined in ideal. And you will get something, C++ with using some C++ 11 features. But of course, you're not going to get lone samples. I don't think the generator can automatically resolve your exception safety issues just like that. You're not going to get the selector. The selector is a really nice way of separating out what you want to read from how you want to read. All these kind of really nice capabilities that we baked into the, it's basically, it cannot replace human intelligence, as simple as that. You don't get overload operators. So many things that are really useful and interesting, improve readability in kind of human designed API. You are not going to get those if you just do direct generation of C++ 11 bindings for DDS. So this is really a suboptimal solution, and I want to put it out there. This is not the way to go. You still need DDS, the PISM, the C++ binding. It's not making our earlier effort, 4 or 5 years effort, redundant. It is, in fact, quite inferior. You could do that, though, if you need for some reason. Well, this is pretty much the last slide, I think. The user-defined types, right? I showed you the radar track data. Those types in C++ 11 environment can use certain language features. I just want to quickly touch upon this specific idiom. This is a constructor. In C++ O3 environment, you would pass const references for these. But in C++ 11, I think it makes sense to pass them by value. The reason is, first of all these parameters here, we know what's allowed in ideal. Ideal has either the basic types, the strings, the sequence that becomes a vector. All these are movable types. We know that in C++ 11. And move is really fast in those cases. Not the array though, so array has an exception. What we do here, instead of, so first of all, you make a copy first of all, obviously. But that's the intent, right? It's a constructor. It really wants to make a copy. So instead of making a copy inside the initializer list, it does it at the boundary of the function itself. And we'll see why that's important. at the boundary of the function, it makes copies of all these, and inside is just going to move all of them to the members. We know for sure that it's going to make a copy, and that's why this works, not in general cases. And constructor is a classic example of that. By making this by value, now you open very interesting optimization for the compiler. If one of these parameters happens to be R value reference, R values actually, a temporary coming from a function, the compiler is smart enough to even construct these. So you're not even making a copy in case of at the boundary of the function. Now, an alternative to that is make all of them R value references. And what that actually turns out to be, you really need 2 raised to 4, 16, yeah, R value references. This could be R value reference, those may not be. These 2 could be R value references, those may not be. You need to spell out all 16 combinations. And that's really the most optimal way. Well, if you have 10 parameters, good luck with that. Well, again, it's generated code, so well, you could generate 2 raised to 10 constructors. I guess that's not impossible or unheard of maybe. But I think that's really unnecessary. And it's kind of really elegant how you pay this cost of extra move, which is a copy of a pointer. I think that's worth it compared to having 2 raised to the exponential number of constructors. So I go into details of this in my another presentation that I did last year in Code Camp. So you could go and just Google if you're interested in how this works, and few other C++ idioms at my Code Camp presentation. So this is what we kind of borrow from ideal to C++11 specification. This is specified. In fact, now it is really implementation dependent, because there are really 2 ways to do this, right? We don't want to constrain vendors to really every single time use this, because the most optimal way, theoretical, is to have exponential number of constructors. We don't want vendors to not use that. If in some certain cases it makes sense to do that, go ahead, be happy, happily you can do that. But I think this is a practical way. So this idea is, this is what we borrow from ideal to C++11 by just using that specification. So if your radar type or your sensor data, and you're declaring it like this, you use the generator, you will get these kind of nice optimizations that are baked into the specification. And I guess that's pretty much it. So if you have some more questions, you can, of course, talk to me. I had my contact information on the first slide. And the slides, actually, I had many more slides than this to fit it in 90 minutes. I really keep my breath, really. I cut down probably 10 or 15 of those. Online, you will get the full set of slides, a few other interesting tidbits on entity QoS and reference counting, how we could how do we use, in fact, we don't use shared pointers because to keep the life cycle of entities. We have to do much more than what shared pointer does because we want to keep the objects around. So those are kind of things I have described. If you're interested, I can talk about it now, or you can go online and take a look when these slides are available. Well, other than that, thank you very much, and this concludes my talk. Any questions, comments?
Just a short question, because I'm new to this. The landscape of these modular applications, how many are there? Are they expensive, open source, open scale?
Good question.
How do you know this?
So the question is this middleware scalable? Is this open source? What's out there in the world, sort of. So RTI, we provide a commercial implementation of this. We have we license this. We also have open community source. We provide you the source code for this. There is a different license for that. There are also open source implementations of DDS. At least I'm aware of at least 2 implementations. And well, I mean, whether it scales or not is really an implementation quality. You know, it really depends. You want to scale in what dimension, right? So it's really, there is no cut and dry answer for this, yes or no. But one thing is for sure, vendors compete on scalability. So that's their value proposition. So you really have to compare each offering, so to speak. Does that answer your question? Yes.
I would just add to that, there's ways you can open DDS but there's no question, I think, that the applications are using at a higher scale. And I think there's a variety of other applications too that are non-military what I was going to ask you though is, so this is relatively new now. So you guys already implemented this? The status of the implementation?
So the question is whether RTI has implemented it or what's the status. We are implementing it. It's not released yet. It's not, I mean, don't quote me on this, but it should be later this year. If everything goes well, that's the plan.
And other vendors are
I hope so, yeah. All right, thanks for coming.